Okay, thank you. Yes, so yeah, when you fill in travel forms for Durham, you're meant to say what you're going to do to publicise your university, and I've completely failed here because I've not only not put my university, I've also not put my name, so I'm not called Philippe 60. That's that's fine. So yeah, it seems that. Well, anyway, yes. Thank you very much for the invitation, and the main idea is to show sort of slightly embarrassing pictures of Philippe, which I hope I will fulfil, and talk a little bit about. So I think I maybe even beat Charlotte in terms of how long. But when I first came here, I think you were mostly in the US. That was when you were on your. But then we met again, and at some point we even shared an office. Absolutely. Which was over there with the nice view of the nuclear waste place. Yes. And yes, and actually, so we're meant to have some vague reminiscence. So I remember for some reason I was doing stupid calculations, and I could never remember trigonometric identities. So I'd written a little post-it note with, you know, sine A plus B and so on. And I came in one morning and there was this extra post-it note down below, which said, well, in French that I'm not going to attempt, surely you learnt this in primary school. And I think I know who put this note there. So anyway, I'm hoping that not too much of this talk gives the same reaction, but we'll see. Good. Okay, so yes, so first of all, there's got to be a slightly fuzzy picture of Philippe, and then there's got to be a picture of Philippe, a bit fuzzy perhaps, so that's with the requisite bottles of wine, and there'll be a couple more at the end, so we can wait for that. Good. So, yeah, I'm really talking here about a sort of long-standing project about just looking at how analytic continuation in complex values of coupling constants work in some simple quantum field theories and trying to get the big picture. So that's the basic problem I'm going to tell you about. And I'll go through some rather old stuff to show the basic ideas of how this goes and try and explain why we've come back to this. So this is mostly work with a recently graduated student, Brandon Morrison, which we hope to write up at some point. And at the end, yes, I'll give some. I think the movies might have to be for a sort of private viewing later, because I don't think I'll get time for that. So there's nothing dodgy about them, but I just don't think I'll have time. Right. Okay, so the basic problem is, suppose you knew, perhaps if you're an integral person, by some exact method, the ground state energy of some quantum system. So can you use that information to find energies of excited states? Okay, that's the basic thing. And quite often the answer is yes. Okay, especially if you can do some analytic, and the particular tactic is going to be do some analytic continuation in a parameter. So I'll show by a completely baby and indeed primary school example in a moment how that goes, and then do a bit more about it. So the spectacular paper on this was Bender and Wu's anharmonic oscillator paper, which got a little bit of shade from Barry Simon later when he said that all... there's some quote which I haven't managed to re-find actually, saying that this paper was kind of remarkable because all the results were correct and all the proofs were wrong. But so anyway, this is very interesting. There's a whole field still of studying these sorts of continuations. And so the big hope would be to get the similar understanding for some quantum field theories, a sort of rather complete picture of how a whole set of energy levels. So what Bender and Wu discovered was a very interesting structure, sort of multi-sheeted Riemann surface, with a sort of systematic structure of where the branch points were, and so on, getting you between at least energy levels within certain sectors. In that case, all of them. In the quantum field theory case, it won't be all of them. So we made a start on that years ago, but I want to go further. So why go back to it now is that when we looked at this before, in fact, probably when I was maybe even sharing an office with Philippe, we managed to find a few low-lying states. So from the ground state, we could sort of, with a lot of pain, continue our way through to a few excited states. But we could never quite see the big picture. Okay? We looked at things called perturbed minimal conformal field theories. Well, people know what a conformal field theory is because everybody has read Philippe's book. And if you sort of nudge them and make them not conformal in a suitable way, you can preserve integrability. This was something that Sasha Zamolodchikov made a lot of interesting progress on. And then you can look at the energy levels of these systems in finite volume and see how they depend on the various parameters and see how the energy levels get connected. But I say, these were sort of somehow too sporadic. We couldn't see the big picture. So the new angle, which I'll get to at the end, but probably only at the very, very end, is to look at the Sykes-Gordon model, which is well, people have probably heard of the Sine-Gordon model, which depends on a parameter which is a sort of radius. The Sykes-Gordon model has a similar coupling. Its Lagrangian just features cosh of beta times the field rather than cos of beta times the field. So in some respects it looks more trivial, but in other respects it behaves in a much more complicated manner. And this extra parameter actually allows you to take a limit when this parameter gets small, and in this limit we are seeing a sort of systematic structure. So that's what I want to tell you a little bit about, and while we haven't completely understood it, what's going on, we think it's quite interesting, and it has sort of thrown up one or two other interesting features and properties of this program of analytic continuation, which I'd also like to talk about. Good. So an absolutely primary school toy model. Let's suppose I have just a two-dimensional system with a Hamiltonian which has got an exactly known bit and a bit which we don't yet know the effect of, so this would be like my perturbation of the conformal field theory. And I look for its energy levels, and I see it's got two separated energy levels, and they're disconnected if this parameter is real, okay? As they have to be, because it's a Hermitian matrix, so we can't have crossing levels. Well, if I instead look at it, I've probably got my lambdas and I lambdas a bit of a muddle here, but if I instead look at complex, and in particular purely imaginary values of this coupling, then suddenly the levels join up. Okay, so the picture in the complex lambda plane, where this is now, I think, whoops, the original lambda, rather than this lambda, is that if I continued this problem around a path in the complex plane round the point I and back again, even if I'd started off at E0, I'd have come back at E1. Okay? And it's kind of clear, right? What's going on is that if you have an eigenvalue problem depending on a parameter, if you continue that parameter round a closed contour, you're going to get back to the same problem, but you're not necessarily going to get back to the same eigenvalue. If you surround some exceptional point where two eigenvectors cross over, coincide and cross over, then you could have a sort of monodromy of eigenvalues, so the set stays the same, but they shuffle around. So you might be able to find another eigenvalue from having the first one. Okay, so it clearly works in finite dimensional problems. And if we're going to try and apply this in quantum mechanics or quantum field theory, let's try and look at a situation with either a confining potential, which is what Bender and Wu looked at, or put our system in a finite box, so the spectrum is still discrete, so it's kind of clearer, we've got a better handle on what we're continuing, so that's okay. But even so, we might worry, and there's actually some reasons to worry, even if we've naively continued round a closed contour. As I'll get to later, there are some reasons why we might be led astray. Turns out that in the Science-Gordon equation, I think we're okay, but anyway, I'll talk about that a bit later. And we won't necessarily see all the other levels in these cases. For example, there might be a conserved quantity like the spin or the momentum round the circle of a state on a circle, which would not be continued when we do this process. So maybe only just see some sector of states. But anyway, we'd like to explore this in some detail, and in particular in a sort of non-trivial model. Okay, so here's a super simple example, though, to start with. If we take the field theory of the Ising model perturbed by a no, definitely not by a magnetic field, by a thermal perturbation, okay? If we perturb the Ising model by a magnetic field, we end up with this whole E8 structure that Zamolodchikov discussed, and that's a whole other can of worms that I don't want to talk about today. But if we take the simplest case of perturbing it in a thermal direction, we actually have a theory of a free fermion, and the ground state energy is known exactly, okay? So here's a rather ghastly formula, but it's not too bad. So there's a little bulk term for the energy, and then the rest of the energy dependence is a sort of overall factor of pi over 6r, which would be the entire scaling behavior of the system were it conformal. But when it's not conformal, you can form a dimensionless number, the mass, or 1 over the correlation length, times the system size, so the system size in units of the correlation length, and the energy can still depend on this. Okay, all the dimensions have been eaten up by this factor, but this is a sort of dimensionless thing, which is sometimes called the effective central charge, because in the case of conformal field theories, it's exactly the central charge. Okay? And there's this rather messy formula. It's this infinite series, but that's actually the one which displays the properties I want most. So this is the formula I'll start with for this function c that comes into E, with there's a little minus sign there. Don't forget that later. Okay? Okay, yeah, and you can see that the levels of this, well, the ground state energy behaves as expected from the sort of predictions of conformal invariance, but I won't go into that too much now. So whoops, actually I've repeated it here. So we've got this infinite sequence of square roots. So we can continue R, so although R is meant to be a real parameter, the system size, we'll now let it be complex. We can continue it around any collection of these branch points, which lie at odd integer multiples of I pi. And if we go round them, we just sort of flip, you know, the signs of the branch points we've gone round from plus to minus, but then when that feeds through into E, because of the various minus signs, that adds twice the corresponding square root that was flipped to the value of E. So once you've gone round this, we don't need to know that whole long formula anymore. We just know that the energy of the state we get to by going around the branch points which are sort of independent of k0 up to kn, okay, so we can take any combination and wind round them, will just be added to by this amount. And this is exactly right for a state of free particles propagating on a circle with beta ansatz quantization condition, okay, on their momenta, and the beta quantum numbers being given by these k's. Okay, so by doing this continuation, we've created a multi-particle state of our system, and actually what we've done is we've created particles sort of two at a time because we have to conserve momentum, so we have to sort of always stay in the zero momentum sector of the theory. So that's fine, and we've understood what's gone on, and we've got ourselves to at least a large subset of the excited states of the theory. Okay, now there's, oops. Yeah, please. Go for it.
That calculation would seem to depend upon the choice of branch cuts, and I could imagine choosing branch cuts so that you're actually encircling something where there's no monodromy at all. How did you choose the monodromy?
Yeah, so in this case, because these are all independent square roots, you just have to sort of count your winding around each square root, and they're just being added up. So in this case, the problem you're worrying about is sort of trivial. You've just got to count your total, because obviously if we went twice round one of these branch cuts, one of these square roots, we just go back again. So it's all relatively trivial in this case. And there's no sort of confusion about going around one, then the other, or vice versa. It's always going to give you the same, because we have an explicit formula for C, where everything is added up. Okay, so in this case, it's fine. But it's a great question, because later on, this is the whole sort of soup we're going to get into when we get to more complicated theories, where things behave in a more complicated way. So this exactly illustrates why this one, although it's showing the basic idea, is way too simple to let us study a case of an interacting non-free theory, where what you've done around one branch cut will then affect whether you see and what you can do around other branch cuts. Okay, so we'll come back. So yeah, thanks. That was. Yeah, please. Yeah, okay, so I basically don't want to go around that. So
my question basically is that if I take in serious this logarithmic cut, would I get another eigenstates which are not of the original model?
This is, I'm going to postpone that. This is going to be related to a bit of problems we'll see later. Okay, so I believe that as we go around the logarithmic branch cut, we get into a sort of different, a sort of shadow sector, if you like. So this would not mean so much. So I think if you eyeball it, it looks like that's not going to give me a sensible answer, but I think we know why. Okay, so yeah, good. But I'll come back to this in another case later. Good. Okay, so there's another way which will be slightly more. So what I'm going to do later, sort of sneak preview, is we're going to have systems where we don't have the closed form for the energy, okay, or for this function C, but we know it in terms of something, a nonlinear integral equation called a thermodynamic beta ansatz equation. I'm going to treat that like a bit of a black box. But that's why I mentioned the word TBA, or thermodynamic beta ansatz, up here. There's another way of writing this exactly known C, which from the point of view of figuring out where the branch cuts are is less useful, but in relation to what's going to come later is more useful. It's got this formula here. Okay, there seems to be oh no, that's the cursor, isn't it? Yeah. Okay, that's fine, okay? So that's just the same function, right? And if we think about what happens to this formula as R becomes complex, you can see this little factor here. This formula might be in trouble if this thing becomes 0, because log of 0 isn't great, right? For some real value of theta naught. So the integration contour, so my thetas are always real for this integration contour, but I could still be in trouble when R becomes complex. Okay, so there could be something wrong there. Okay. Well, normally we'd be fine, right? Because you can if you've got a singularity approaching the contour, we can just distort the contour down a bit and continue. And so everything is going to be a smooth function. We've just got to pay attention to whether that's happened or not. Okay, so the continuation will be completely smooth, and this would not mean that there's any sort of singularity in the actual function being described. It just means we've got to be a little bit careful about how we describe it in this, for these values of R. We probably have to have an extra term in my C. Okay? Well, where does this go wrong? Well, actually, you can see from these formulae that the singularities are always symmetrically placed between sort of theta and minus theta. And so it could be that two singularities collide either side, and that's what's known as a pinch singularity in the sort of, in the 1960s, analytic S-matrix days and so on. Okay? And then there's nowhere to go with your contour. You can't go up or down, you're stuck. Okay? And that's exactly what generates the branch point. So you can check that the places where the values of R for which this happens, and it has to happen at the origin, are exactly the places where those branch cuts up the imaginary axis were. And if you do a little sort of dance around a branch point, then these singularities will sort of do a little loop, and untangling the loop exactly generates the discontinuity across the cut. So that's all very easy. Okay? Now, as I said, in general, we don't have a closed form for this E0. Okay? But in integrable quantum field theory, so it's too much to hope to get any sort of big understanding for a non-integrable quantum field theory, but at least in 1+1 dimension, so like this Ising case, there are other examples of interacting quantum field theories where we do know an exact formula for this ground state energy, but only in terms of things called TBA equations. Okay? And we're going to see that this is enough to get ourselves to what's called, to see how these equations change when we go around these branch points and get us to new equations describing the excited state. So at the moment I'm still describing rather old stuff. And maybe I'll not get beyond that today. Anyway, so the analog of having my, 1 minus 1, my exactly known Hamiltonian, would be the conformal field theory Hamiltonian. So I'm taking the very simplest perturbation of a conformal field theory, which is the M25. Go and look in Philippe's book for more. And I'm adding on to it the single primary field apart from the identity in this theory. So that's creating a theory which is actually a massive theory, and for certain, actually it turns out lambda negative, depending on your conventions of how you normalize OPEs and fields and so on, then this is actually a theory of a single massive particle. So my states of this theory when the system size are very large are a bunch of massive particles flying about, and when two of these particles cross each other, they scatter with an amplitude, an exact S matrix, so this is the scattering amplitude, so two particles always go to two particles, 3 to 3, and so on. But at each two-particle interaction, depending on the rapidity, you get this rapidity-dependent sort of phase factor coming in. Well, the S matrix is e to the phase factor, which is given by this little exact formula here. So it's got a pair of poles, actually, anyway, that's the function. Okay? And this has been verified by all sorts of ways. And the recipe then, so this is just the rules, okay, we can't argue with these. This was, well, dates back way to beta ansatz techniques, but in the relativistics context was first really exploited by Alyosha Zamolodchikov, shortly after Sasha started studying perturbed conformal field theories. You have to solve this little integral equation. So this isn't it for this auxiliary function epsilon, which is called the pseudo energy. So it is a closed equation because this L is log of 1 plus e to the minus epsilon. Okay, so this is a little equation for epsilon, and and you can solve it in various limits, and the system size comes in this sort of driving term in the equation here. So you solve this equation here, and then C is given in terms of the epsilon that's solved, in terms of this function here. Now for the Ising model case, the S matrix is trivial, the S matrix is -1, so this factor phi is just 0, okay? It's a derivative of a constant, so epsilon is r log, epsilon is just r cos theta, and this gets me back to the formula that we had before, okay? So it's consistent, but now there's this extra step where we have to find this pseudo energy as well, but then the energy has a similar form to before, okay? And there's, yes, this bulk term, as I was saying before, we don't really care about. Okay. So usually we solve this equation with R being real, but there's nothing to stop us from making R complex and just lobbing the thing, at least as first go, on a computer and just plotting a little sort of grid of what this C function is everywhere in the complex plane and just see what you get. Okay, that's what we did years ago. And here's a plot of what you get for the Yang-Lee model. Okay, so real values of R horizontally, complex values vertically, and you see a couple of places here which certainly smell like branch points. Okay, so there are a couple of branch points in the thing. I don't know what a branch point smells like, but anyway, they look like branch points, okay? And in fact, there's a sort of little straight line where the imaginary part is also 0 here, where the C function is real, and that corresponds to negative values of the coupling. So everything kind of hangs together. Everything is consistent with expectation, but there are these branch points, okay? But now, as we continue round these branch points, not only is that formula for C going to have some monodromy, but also possibly because the equation that's being satisfied by the epsilon function is also in danger of having these sort of poles crossing contours phenomena, there's a danger that the equation for epsilon will also undergo monodromy. In fact, that's what we want. Okay? So the basic mechanism, I'll scoot through this fairly rapidly, but the basic mechanism is that this, as before, this L will have some singularities, okay? And in general, these are going to be clear of the real axis, but we might have a situation where they approach the real axis as R varies along the path, in particular as R goes round a path encircling one of those branch points we just saw. Okay? So here's a situation, sort of a snapshot from a movie maybe, where these two are approaching, and then this term in the TBA equation, which was a convolution term, is in danger because this term here has a singularity. Okay, so what you do, step one, you distort the contour as before. So now your TBA equation has an instruction that you have to solve this convolution along this twiddly contour instead, and that gives you the genuine analytic continuation of the equation you first thought of. Okay, so that's certainly going to give you the right answer, but it's not very transparent what's happened. So step two is you return the contour to the real axis, and now you've got a couple of little extra bits of contour going around the singularities. Okay, and it turns out by sort of luck, after you've integrated by parts, you get the sort of singularity term here. So my singularity is when this term here, which was part of the L was 1 plus e to the minus epsilon, when that thing is minus 1, that's when the singularity is going to occur. And this is just the right form that it's got a residue minus 1. Okay, it's just kind of neat that it works out that way. So you just spit out an extra term. So you can evaluate these residues explicitly in terms of the value that this bit has at the location of the two singularities. Okay, so now we have a modified equation, a modified TBA equation, which looks like this. So it's like the old one, but with an extra term here, which is somehow encoding the fact that we've now in a different world where we're looking at an excited state. And you can do the same calculation for the C function, and you again get an extra term here, which is going to sort of turn into the, well, in this case, it's going to actually be a one-particle state, and it's going to sort of give us the mass of that state in the large R limit. Okay. And the equation seems to have an extra unknown, right? There's this theta 0, the location of the singularity. But there's also self-consistency condition, which is that this thing must be 0. So we get a little self-consistency condition. And there's to satisfy that self-consistency condition, there's actually an integer here that we get. And that maps into these beta ansatz quantum numbers of our states that we get, of our new states that we get to after we've done the continuation. Okay, so that's the basic picture, that's the basic mechanism. And the natural question then would be, well, can we iterate? Can we repeat this process? Okay? Can we now start with this? Well, let me just say. Can we find out how the states say with different, we know there are different options for the n that we generate at this point, which, branch point by branch point, we can find out what these n's are. But can we then iterate it and generate states with maybe two quantum numbers? So corresponding to actually it would be maybe two particles on the torus or four. Okay, so the big plan would be to start with the ground state TBA, continue it to find these first state TBAs, and maybe depending on the particular branch point we go around, we get different values of n. Okay. But then from those, do the same. So then we go back and we study their branch points, okay, which may be in a different pattern. So this is a bit relating to the first question we had, and bootstrap ourselves perhaps to the full Riemann surface of this function C, which, okay, maybe nobody else cares, but I'd quite like to know what these surfaces are. Okay, so that's the thing. Now, unfortunately, it's hard. Okay, so one of the problems is that the numerical, as you saw perhaps from that, well, it wasn't very clear actually because we swept the problems under the rug in that case, but in general, and as you'll see in my pictures later, there are whole regions where the numerical iteration of these TBA equations, which you tend to do in order to find these solutions when you can't do them analytically, just breaks down, okay? The iteration stops converging. And actually, in the case of Sykes-Gordon model, you can get some quite sharp results about where these breakdowns will happen. Okay? And in particular, it's particularly bad near branch points. I mean, it's a standard phenomenon when you're solving equations iteratively. When you have collisions of roots, then solving them by iteration becomes difficult. Okay? So, and furthermore, somehow these isolated cases like the perturbed Yang-Lee model, perturbations of other minimal models that we looked at, they're kind of a bit too special. So there's a kind of random pattern of these branch points, and as you go around one and then another, you ended up somewhere else with a whole different pattern and so on. So we could never really spot the full picture. So instead, and for the rest of the talk, I'll try a different model with more structure, which will actually give us a little bit more of a toe hold, or no, that's not a toe, the finger hold on what's going on. We'll look at Sykes-Gordon instead. Okay? So again, unfortunately, in spite of the title, I'm going to say very little about what the Sykes-Gordon model is, apart from the instruction is again a theory with a single massive particle state. So if we think about states on a circle, they'd just be a bunch of particles sort of circulating around at large distances. When we squash the system a bit, because it's an interacting quantum field theory, then things become a bit more complicated. It's not as simple as the Ising model anymore. And the S matrix looks sort of deceptively simple, and we'll see in a little bit some reasons which actually relate back to more sort of cluster algebra type ideas. Little hints about why actually the behavior of this is far more complicated than for the simpler perturbed minimum models that people had studied in great depth. Anyway, so this S matrix has zeros, or not poles, zeros. There are no bound states in this theory, at values of this parameter p, which goes between 0 and 1, at I pi p and I pi 1 minus p, maps to itself there. So the TBA is just given by the same recipe as before. And this gives us a representation of this pseudo-energy function in actually what's a rather narrow strip when p is small, okay? Because you've got singularities in this kernel function corresponding to singularities in S. Okay? So that's kind of troublesome. That's going to make it rather harder to look at. But luckily, Alyosha Zamolodchikov analyzed this system in great detail, and so there's a very nice paper by him about the TBA equations. And his approach to this, so this is where we get to things like Y systems and so on, his approach was to introduce, so normally for these TBA systems which get related to things like these Y system conjectures, you introduce this Y function as actually in those cases it's e to the plus epsilon, okay? And then you find these very nice functional relations, and for example these sets of functional relations related to ADE that Francesco found these nice periodicity results for, which were subsequently proved by, I suspect, other people in this room. But in this case, the clever thing to do is actually introduce a pair of functions, y and x. And this x function, the big difference is the kernel is different. Okay? The kernel's got this 1 over cosh again. And so this function is already well defined on a much wider strip, which doesn't get narrower as p tends to 0. So that's kind of good news. Okay? And he established these bunches of functional relations. Okay? So the x functions obey this functional relation. The y is this, and then there's sort of combined relations between the two. And these relations can be used together to reconstruct from knowledge of this epsilon function just on the real axis, the function on the whole complex plane, which is what we need to keep track as to whether anything's going to be going wrong in our continuation of the TBA equation, whether we're going to need to introduce extra terms. Okay? And just highlight, and this is, well, let's look at the X system here. It's particularly curious because you've got shifts, okay, in the parameter, but they're both in the same direction, okay? They're both in the complex direction, okay? So you've got A, which it can be a general real number, okay? So not necessarily commensurate with 1, okay? So you've got two different shifts, but they're happening in the same direction. They're also happening at right angles. And so this gives an extremely complicated structure, as a hint of an extremely complicated structure to the solutions of these equations. So you start off on the real axis and you try and use these X systems and Y systems to reconstruct. And they just get more and more complicated for general values of A or P as you move away from the real axis. Okay? And particular smaller side is that if we take the simplest case of this, which would be the self-dual point P equals a half, okay, then this is just x squared, so the relation becomes that, which is actually a known thing. That's the recurrence relation to the cluster algebra apparently of type A11, which is the simplest infinite cluster algebra. So I was kind of quite pleased with myself because I actually managed to solve this thing. And I was talking to Pavel Tomarkin, who's also in Durham. He said, yes, there's this paper by Zevlinsky, which has done it. So anyway, but so this one can be solved exactly, and you can find a rather complicated formula for how this recurrence goes in terms of initial data for it. But I think in more general cases, it's just not, explicit formulae aren't known. There's no simple periodicity, as with these Y-system periodicity conjectures. There's no before. And this is a sign of a more complicated structure of these models. Okay. Anyway, I don't want to look at the self-dual point. I want to look in the opposite direction as p tends to 0. And there's one particular simplification that happens in this limit, which is that this kernel function just concentrates near theta equals 0. And you can replace it, at least on your initial contour of integration, by just a delta function. And then you can solve, and so you can find the epsilon in closed form. Okay? And I think, well, given the time, I'm going to just focus on this one thing and then skip a bit. But anyway, so this would give you what looks like the limiting form of this function c. Okay? And I'm just going to highlight one little thing that made us think that we'd gone completely off the rails here, and then we've decided that things are okay. So this resembles very much that formula I gave you for the Ising model central charge, okay, but with some sign flips. And in fact, it's the effective central charge for a free boson on a circle, not a free fermion, okay, which is kind of what you'd expect, because the Science-Gordon model in this limit should correspond to a free fermion, a free boson. So that's not surprising, but there's a problem. So the problem is that we can also find an infinite series representation of sum of square roots for this C. So I think a paper by Hubert and Claude, and then Klaas and Melzer paper looked at the free boson. Actually, Seller-Itzigson was looking at the thing on a torus, but you can extract from that what the ground state is doing. And the Klaas and Melzer paper also uses their results, I think. And you get a similar looking formula with a sequence of branch points, okay, here. So it's a bit similar to the Ising formula, which is what I've written down here. But there are two differences. Well, okay, the branch points are at even multiples of I pi not odd. That's not a big deal. But the signs of the square roots are opposite, okay? Well, when we did this continuation in the Ising model, okay, the flipping a sign of this square root, once you sort of chase back where the minuses are and the pluses, increased E. Okay, so it gave you a state with a higher energy. That's good. But in this case, since we started off with the opposite sign, we're now going to go the other way. So now we've got states which have lower energy than the ground state, which is bad. Okay, well, okay, so now why did we convince ourselves that this was fine? And this is a little bit, I think, like continuing around the origin. So let's take a toy example. Let's have a free boson in a universe with just one point. Okay, so it's a simple harmonic oscillator. Okay? So usually your spectrum is defined by demanding that these wave functions should be square integral on the real axis, okay, and then the energies are odd multiples of this parameter nu. Okay? But if we set nu to be a complex number, okay, so R real e to the I phi, and continue phi from 0 to pi, okay, then the nu squared that appears here continues back to itself, okay? So nu goes to minus nu, but nu squared goes to itself. So this Hamiltonian just goes to itself, okay? But if you look at the formula for the energies, you can see that since nu went to minus nu, all the energies have gone to minus themselves. So that looks a bit weird. Why did that happen? Well, okay, there's a story of Stokes sectors, which I'm also running out of time for. Yes, I think I want to show some pictures. So I'll scoot through this a bit quickly. But essentially, there are directions in the complex plane on which we could consider our wave functions, where the eigenvalue problem breaks down because WKB wave functions are both oscillating. And as you continue your eigenvalue problem, you have to avoid those lines. So essentially what happens is, as we continue, okay, so I'll be a bit quicker. As we continue nu in the complex plane from nu to minus nu through these values, well, nu squared goes back to itself. But these dodgy lines along which we're not allowed to have our integration contour actually rotate by just a quarter turn. Okay? So in order to continue the eigenvalue problem correctly, our contour of integration has to also follow that round, otherwise we haven't continued it correctly. And now we've got a different problem where we're quantizing this system where our wave functions are square integral up the imaginary axis, which is obviously a bit nuts, but anyway, that's what we've got to. And that's why the eigenvalues have gone negative. Okay? And the story is actually the same if you take a coupled pair of harmonic oscillators, or even if you take an infinite chain of coupled harmonic oscillators, you get the same picture. Okay? So we claim that this is what's happening for the free boson. Essentially, the continuation is messing up the boundary conditions at infinity. Okay, we're switching to a different sector. So although the operator looks the same, the full eigenvalue problem for these sort of infinite dimensional cases includes boundary conditions on the differential operator at infinity. And we've got to make sure that we don't mess those up. But we don't expect to see this for Science-Gordon because the growth in the potential here is much greater. So that reassures us that we should be safe. And confirmation comes from the numerical work I'll report. But that does mean that this p to 0 limit is very subtle. Okay, and that's something that we don't fully understand yet and would like to understand. How much longer have I got? About no minutes. 3 minutes, okay, so I'll show some pretty pictures and then we'll stop. Okay, so the pretty pictures may or may not include the pictures of Philippe, of course. Anyway, I make no comment. Anyway, actually I've got him looking slightly more cool than some of the other ones. Right, so so these are the pictures. This is the same sort of plot, a scan, as we showed for the case of the Yang-Lee model earlier. And we see a rather rich pattern of branch points, but the system, so this is p equals 0.04. As p gets even smaller, so we see that we already see these sort of, by the way, yeah, so this is this region, these regions I was hinting to you, where the equations just don't converge by iteration. If we were more clever, maybe we could do it, but we can't. And that, you can see the sort of slight shape developing here about where we can't converge. Well, that's the thing you can control analytically to at least understand why we don't converge, but I won't go into that today. So as p tends to 0, we find these pairs of branch points sort of joined together. Okay? So that's, again, a systematic picture that we were lacking in our previous studies. Okay? And each of these pairs connects either way with a two-particle TBA solution, so two particles of my Science-Gordon model. So we're starting off here with 0 particles. This is the TBA equation describing 0 particles. We connect to 2 particles with steadily increased momenta of these, quantized momenta of these things around the circle. So quantum number 1, 2, 3, 4, and so on. Okay? So that's the picture. And then if we continue round one of these branch points, we can then find an excited state equation. So say round this one, you're meant to see that this point here is the same as this point here, plus or minus, okay? And these are equations describing 2 particles moving relatively slowly, or we could find the equation with 2 particles moving a little bit more quickly. And the structure of these other branch points do not agree. So again, this is answering a bit the question from the beginning, is that now depending on which branch point we went round first, we'd see different branch points later. Okay, so this is why it's much more complicated, but at the same time maybe more fun to explore. And you can sort of have fun trying to make 3D plots of how these levels go as well. And the real fly in the ointment is that in doing all this, we found a sort of extra sequence of branch points converging towards some of these. And I think this is to do with the subtleties of this p to 0 limit and how you have to sort of somehow slice off to avoid the behavior of the free boson, which is what you don't like. So this limit is subtle. And we haven't managed to get the damn equations to converge enough to get a really good handle on that, but we know it's there. So we're going to be studying this more as time goes by. And then we can see the structure. So this is a bit of a, I think this is not going to be very explicable, but this is a structure of the, in the complex plane of these pseudo-energy functions. And in particular, places where you see little sort of, well, if you look really closely, you see little rings of, so these sort of little highlighted points here, are places where the TBA equation would break down because e to the epsilon is -1. Okay? And there's a rather curious structure. So Zamolodchikov in his papers predicted that you would have, so you can't see it here, but there are lines of these special points vertically here. But the surprising special structure is as p tends to 0, these lines sort of bifurcate, and there seems to be this accumulation of zeros along an interesting pattern of lines. And if anyone has seen this before for Science-Gordon, please let me know, because I haven't found it anywhere, and I'd like to understand it better and probably analytically. But at the moment, we just have numerical data on this, and this seems to be what happens. So again, it's a sign that this limit is quite interesting. Okay? And for an excited state, you kind of have the same thing, but there's a sort of little gap in these things corresponding to exactly where the momentum of this new particle is that we've created. So you have states with 2 particles, states with 4 particles, where we have 2 of these slightly funny points and so on. Okay? And as R leaves the real axis and wanders about, you get sort of nice movies. How much time have I got now? I've got no minutes, really. Yeah, okay, so the movies are for later. So anyone wants to see a movie, they can ask me later and I'll show you. So you can see little pictures of these things sort of dancing around as we go around these little branch points. But I have to leave the audience vaguely wanting more, so I'll stop with that. So the conclusions are, well, this limit does indeed show regularities, which gives us hope that we're going to be able to make a more complete picture. But the way the limit works is more subtle, and I think I probably need slightly more powerful analytic techniques to really understand what's going on. And it would certainly be interesting to understand other models in a similar way. And one of the things that Alyosha in his papers was interested in was a particular limit of Science-Gordon called the staircase model, which I also, with Francesco, enjoyed looking at back in the day. And I think there'd be definitely more to do with that. Okay, so that's all I have to say. But I have a happy 60th greetings to Philippe, with a picture of Philippe at about 40, I think, maybe 39, I think it was in March 2004. So, and that's actually, I think he's back at École Normale today, but you might recognize the other person too. It's Kay. Good, and that's Philippe looking relaxed after the skiing. Much more relaxed than I was, actually, to be honest. Okay, thanks very much.
Okay, good. There's a question. you mentioned briefly the case of the Ising model perturbed by the magnetic field. So can you say a little more about it?
Not much. I mean, so, yeah, we tried a bit. So essentially, well, what we found, first of all, so this is way back in the day, again, probably when we were colleagues in Saclay, even on one of my revisits. So we tried, first of all, looking at perturbations of this sequence of non-unitary minimal models. Okay, so Yang-Li is the first example, but then you've got M2 to n plus 1. Okay, and what we realized is that actually the structure of these extra singularities in the equations is rather complicated. So even to describe a single particle state in these more complicated theories with more different sorts of particles, you maybe need 2 or 3 of these extra singularities which together describe that single particle. Okay, and then you have very curious sort of sum identities which enable everything to add up to give you exactly the correct mass of that state coming out from your equations when you look at a large system size. Okay, and for E8, we got as far as finding the corresponding sets of little sum rules and finding that the equations would involve little clusters of these extra singularities like these theta zeros, even for the different single particle states. But again, we didn't see the general picture, and the E8 looked even worse to understand from that point of view to Ising. So I'm sure there's a nice picture ultimately, but we don't know it. Okay.
Behind you.
Yeah, I have actually 2 questions. From what I understand, in the weak continuation you are doing, the small parameter R, actually it was a weak continuation of the coupling constant of the theory.
Yeah.
And then these last 2 examples that you gave for Lee Young and for Singe-Gordon, the difference in one case, the first case, you got ground state energy, which was kind of function with infinite number of cuts, and you're going around the cuts to get to steady states. And for second one, it was function with the stock lines.
Oh, no. It was still, no. Sorry, yes, this is a little bit confusing, but we weren't continuing, well, okay. So that was for my the Stokes line were in my little toy example of just a single boson, so a single harmonic oscillator. And that's not really relevant for that's a different, that's sort of looking at the wave function explicitly, so that's not the same as the quantum field theory case we were looking at. So no, for the quantum field theories, it was basically the same picture for both cases.
Okay, but then imagine I'm starting with ground state energy, functional coupling constant. And then I go continuation to negative value of the coupling constant.
Yep.
So you're talking about continuation which is going to the complex plane as a complex quantum.
Yep.
I go to negative coupling constant. And then there's an argument by Dyson telling you that at that moment you will have to cross stock line.
Yep.
Did you look into this? What will
Not yet. Well, I think in some sense this is, we would hope that, so what Bender, so, this is basically, and then after Dyson, then Bender-Wu made this very explicit for the case of the quantum mechanics of the anharmonic oscillator. And so one would hope that when we get a more detailed picture of the full structure, so you have to see all these branch points which are probably getting, as you dig deeper and deeper, they're going to get closer and closer to R equals 0. And that's going to explain to you why going to negative coupling, for example, is bad. But at the moment, we're like baby steps, right, or primary school steps. So we haven't.
But in principle, this fellows.
But in principle, one would hope to get a similar picture. Yeah, definitely, definitely. Oof.
That was a nice catch. Any other question?
So in the Singe-Gordon model, the perturbation has a negative conformal weight.
Yeah.
You would expect to see this in a finite size spectrum, maybe.
Yeah.
Meaning
So I think
eigenstate of energy lower than the ground state, which is.
Well, I don't know. I mean, morally speaking, I mean, so Alyosha frets a lot about that in this paper. And I think, so essentially the thing is defined, so essentially we're starting from the other end. So when you do the TBA, you start with a large system size specification of your theory, and then you get an exact equation describing the ground state energy from that. Okay? And at least by doing our sort of geographical explorations, we haven't seen any signs of states with the wrong energy. But what does happen is that the UV behavior of things like the ground state energy is much more complicated than it is in a case like Singe-Gordon. And that's a bit because these periodicity conjectures, so these periodicity results for these Y functions, do not hold here. Okay? So that's part of the reason why this structure is much more complicated. And you saw, even the self-dual point had this A11 quiver structure. So it's a kind of hint that so in some sense the Singe-Gordon model is much simpler than Singe-Gordon in the infrared and much more complicated in the UV. And here's the whole sort of challenge.
Thanks.
Okay.
Okay, I think it's time to go on. So let's thank again.